Hello, everybody, and welcome to GlugNet. My name is Stephen Ball. I am the president of GlugNet. Tonight, we are pleased to be joined by Kendall Miller, who will be talking to us about scaling systems. But before we get started with that, a few housekeeping items. Who is GlugNet? GlugNet is the Greater Lansing user group for .NET developers. We are currently based out of Okemos, Michigan, as pictured on the map here. Our meetings are held every month on the third Thursday. We are free and open to the public. The best way to find out more information about our upcoming meetings is if you visit our meetup page, meetup.com/glugnet. We are always looking for lightning talks before our speakers. So if you are interested or somebody you know might be interested, you can either contact myself or Joe Kunk, and we will get you scheduled before one of our upcoming meetings. We would very much like for this presentation tonight to be interactive, so if you have questions at any point, you can come off mute and ask your question. If you are uncomfortable or unable to do so for whatever reason, there is also a chat feature in GoToMeeting that will be monitoring for questions along the way. Otherwise, we ask that you please stay muted so everybody can hear and enjoy the presentation. At the conclusion of tonight's presentation, there will be a survey offered to all attendees. This is completely anonymous. We are looking for two things. From an organizational standpoint, how did we do about getting the word out about this event? And for our speaker, what did we like, what didn't we like? All feedback received is completely anonymous, so your honest feedback is greatly appreciated. And Kendall, a copy of the results will be sent to you after that's closed.
Excellent.
Our sponsors for this evening, NIS Technologies, who is providing this go-to session, and the .NET Foundation, who helps pay the bills for the organization. Our meetups are typically recorded. I say typically because not all speakers agreed to it, and we completely understand why. But those that are recorded end up on Sam Nasser's YouTube channel. So you can go to youtube.com/@SamNasserMVP or use the QR code on the screen to find some of our past recordings. Additionally, if you are attending this, some other meetups that you might be interested in, the Cleveland C# user group. I did not get a chance to update this slide, but I happen to know that they are going to be talking about OpenAI this month. So you can go to their meetup page, the link's right there, if you're interested in attending that event. The Greater Lansing area for SQL Server. At this time, I don't believe they have anything scheduled, but their link is there as well if you were interested in that sort of thing. MI.net, they are an in-person only event in Southfield, Michigan at Epitech headquarters. They're going to be talking about idempotence and software development next month. So if you're in the Southfield, Michigan area and that sounds like something interesting, the link is right there. You can feel free to join them. And now, as they say, it is time for our feature presentation.
So first off, thanks to everybody for coming. I appreciate the opportunity to come and speak with your user group. This is a talk that I love to give. I love to be conversational as well, because what we're going to talk about today are evergreen concepts that will work the rest of your career, regardless of what new technologies come on the scene, of how those things change. They're fundamentals, but these fundamentals are items that we often don't realize that they're there behind the scenes because we use the tactics that spring from them, but those tactics will change over time. Since I wrote this talk originally, a number of things have come and gone on the market, but nothing in this talk has changed really. And that's a great thing because it means it's something you can fall back on over time as things go. With that then, let me start off just a real quick introduction about myself. Great. So I'm Kendall Miller. Hi. You can see my contact info there on the left, particularly the email address, kendall@kendallwmiller.com. If you have any questions after the talk today, or anything else I might be able to help you with, I love to talk with folks. There's actually on my portfolio site, kendallwmiller.com, there's a schedule link in the upper right. Just hit that and schedule some time. Let's talk about whatever you're thinking about. My background, I am a CTO, COO executive for SaaS startups for a little over 20 years. Been doing a range of startups, both my own, working for others, consulting on them. And in fact, I'm looking for my next challenge right now. For folks who watch me on LinkedIn, you'll notice I put my available for work up just early this week. So always interested in hard problems. I tend to specialize in growth and turnaround situations for tech product companies. I myself, although I still code, I pretend in a business context like I don't, so that I can really help shape larger teams and help them get outsized results. My own technical background, I got my career start actually with a degree in computer engineering from the University of Illinois Urbana-Champaign. And we were talking earlier today about systems thinking. It's really a passion of mine to always look at any detailed item and back up to what is the larger system that this is a part of, and how does it all work together to achieve more. So with that, let's lay a little foundation. So first off, fair warning, if you came today expecting to see a bunch of code about like how to write a very specific scalable thing or configure Kubernetes or something like that, we're not going to do that. There's literally no code in today's presentation. And I think that's a feature, not a bug. So with that, let's do a little ground setting. So if we're going to talk about scalable architectures and scalable systems, we need to define scalability. And this is actually a well-reasoned definition I didn't come up with. There's a wonderful Microsoft research paper that underpins a lot of the things you're going to see in the presentation today. And scaling is the ability to cope and perform under an increasing workload. That's their definition. And it works. It really works when you pull the pieces apart of it. So what are we talking about there? So to scale means that you can cope, or basically meet your criteria for success, under an increasing workload. So you are said to be able to scale as long as we increase the workload up to some limit, you are able to keep performing under that workload. So what is scaling to a load? It's available, sustaining that load. Now, what's available mean? Well, when we say available, I need to move that. Being available is about being able to complete a request in an acceptable period of time. And this is actually a first sort of checkpoint when you think about your applications. I've been there with IT groups and development teams where they've said, like, what do you mean the system's down? It's not down, all the lights are green, blah, blah, blah. Well, yeah, but it's taking a minute to respond to requests. Nobody's waiting a minute for the page. They moved on. And if they type in your domain name and nothing comes back for 30 seconds, you were down. It doesn't matter if 30 seconds after they left, you returned a result. From the standpoint of the user, you were down. So being available isn't necessarily what the perspective is from our server side or the back end of what happened. It's really a criteria expressed. What is the longest time you can take for the outside observer to wait for an outcome before they decide you are down? And that's a surprisingly variable thing. If you think about, for example, web requests or some items like that, we have relatively short criteria that will allow. On the other hand, if you're doing a large running process like, I'm going to go and request a report of the full history of all sales transactions by region internationally, that I know is going to produce a 100-page report, and it takes an hour for me to get an email saying, okay, your report's ready, that may be perfectly available and perfectly fine. So it doesn't mean it has to be very fast. It just means it has to be completed in an acceptable period of time. And that leads us to, we have to be able to define that period of time. So, and the scale element. So we have to define two things ultimately before we even really talk about making our architecture scalable. The first one is, what is the request per unit time target that we need to build to? So in other words, as we're increasing the load, how far up does it go that we care? Because if it's not a load we'll ever experience, we don't need to worry about our ability to handle that load. And then the second element is, how long will we wait for that response? What is the maximum latency we will accept before it's considered down? Could be web requests, could be very, very short, could be under a second. Reports or other, I don't know, transaction confirmation emails or order emails, maybe it's allowable to have it be hours. So those two are inputs that have to come from somewhere outside the development team. And that's really my first checkpoint here. When we're talking about making your architecture, your application scale, you need to have a conversation with your customer, your business user, or your outside party to establish these two criteria. And you'll probably have multiple sets of them for different parts of your system. You need that from them, because ultimately the contract's going to be, they tell you that, and then they're going to have to pay for what that takes in your engineering time, hosting time, and everything else. Because all the work we're putting into making our system scale is work we're not putting into something else. It's work we're not putting into usability, functionality, anything else our dev team might be spending time on. Now, I have never met a dev team that had time on its hands. I'm sure it's conceptually possible that there are teams out there that do. That they've got plenty of time. It's not an issue. They're just looking for something to do. So why not make it faster? But I've never worked with one of those teams. So we have to have these targets that come from outside, because we're going to invest their engineering time or their engineering funds to get to them. And then once we've met them, that we kind of need to stop, because while we're investing in this, we're not investing in other things. So how do you get there? Well, here's a little bit of context. Let's talk about just requests per unit time. And I'm going to give you some perspective here. So if you start at the top, how many requests per second do we need to do? And let's baseline some different ideas here. Let's say we were responsible for, say, Twitter or Amazon. They get, roughly speaking, from public numbers that I can use, about this number of visitors per day. So if we just take like Amazon, 75 million, so 75,000 visitors a day. Microsoft in their core platforms, is not Azure, it's really the Microsoft.com sites, believe it or not, 36 million visitors per day. Now, you notice that the numbers didn't fall off a lot, like Stack Overflow, 6 million visitors a day. Target Corporation, 4.6 million per day. Meijer, grocery store, right? 35,000 a day. And because, of course, we're huge, one of my products that my company, that I'm still on the board with, Gibraltar Software, one of the products we make and maintain, Loop, not the actual SaaS platform, but all of our marketing sites, we get about 1,000 visitors a day. So that's visitors per day. Now if we cluster this a bit, I want to show you this picture a little differently. If you look at it using a base 10 log scale as opposed to the absolute numbers, you can actually start to see some grouping happening here. You have what I would call the ultra scalables at the top of this chart. So these are in the tens of millions of visitors per day. If you work for one of these companies, you can get your evening back, because I'm not going to tell you anything that those companies don't already well know. You don't get to these numbers without knowing these aspects of it. And then even then, you get down into the these are the scalables. These are the super scalables. So here you're talking single digit millions, 1 million to 10 million visitors a day. And then we're into sites where we get in numbers we can really manage. Meijer, Loop, number of visitors per day, pretty reasonable numbers. And I say this, by the way, because we're going to go do the math, and you're going to see how few requests this actually boils out to be. There's a tendency, in my experience with customers, with businesses, that they way overstate how many requests per second your system needs to be able to handle, and we as engineers way over pursue it. So let's just take Meijer as our stalking horse example here. So 35,000 visitors a day. Applying some rough industry metrics, that's about 175,000 dynamic pages per day. Now I'm doing a little bit of a shift here, because I don't care about graphic assets and things like that. In the year of our Lord 2024, if you're slow hosting graphic assets or CSS or something, that is a completely solved problem, and we're basically going to wash our hands of it in the conversation today. But 175,000 pages per day. Now, if we assume that there's 11 high traffic business hours a day, so that's the eight normal business hours plus time zones coast to coast, etc., That's 16,000 pages an hour. That's 4.4 pages a second. And that's the thing I want you to sit back and think about for a minute. 4.4 pages a second. So that would mean if I had a single core, single processor web server, as long as its median time, its P50 time to calculate a dynamic page was 200 milliseconds or less, that one server is exceeding this target. That's a very low bar. It's a really low bar. And in fact, I think in a lot of ways, it's sort of humbling to back and think about like, yeah, so why aren't all sites fast? 200 milliseconds is an eon of computer time. And yet we have performance issues. So setting this target though is really huge, because let's say, for example, if I was looking at these numbers, I might say like, okay, I need to be able to make sure that my P50 time at 5 pages per second is under my key criteria, and then I know I have scaled to that, because they're only actually steady state running that number. Now there may be bursts, there's whole set of things around that, but you get an idea of like, this is a small number. And this is how we were, you go back 20 years, where a web server was a 600 megahertz single core system. We were able to build systems that easily handled, double this traffic on single servers. So how then, we set a goal. We need to know what that is as an organization. And then we do the engineering to get up to that point. Meyer may still be using 600, and that's just called efficiency in capital spending. That's what that is when you're still using 600 megahertz single core servers. So, all right, how do we solve that problem? Well, the obvious answer is that we adopt, these specific architectures. I'm sure we've all seen talked about. We're using MapReduce. We have a backend for front end with our application. Throw some Kubernetes in there and some load balancers. No, actually, we're going to do none of this stuff. These are all tactics, and we're not going to really dig into in any one of these individual items today. And instead, we're going to look at the fundamentals that you can build up to actually, given any set of current technology, figure out what is your next move if you're not making your target. So we set the target. Hey, we need at 5 requests per second, we need to be under, say, 100 milliseconds. That's our acceptable target. So how do we get there, and how do we stay there? And it all boils down to something very simple to remember, which is AC/DC. It's a simple mnemonic we can use to remember all the aspects we'll ever have to worry about in our careers about making something scale. So what does that stand for? Well, the A is async, doing the work at some time other than the moment of the critical request. So do the work whenever. Don't couple it to the time critical period. C is caching. Don't do work you don't have to do. Reuse work that you did before. D is distribution. Get more people and parties to do the work to scale out. And then at the end of the day, C, consistency, is what stops us from scaling. So A, C, D, those three techniques are all we have to make a system scale better. And at the end, we get stopped by the consistency rules we create for the platform. The more consistency rules we create, the harder it is to apply any of the other three. So it's the tension between those two that ultimately is what manages and controls our scaling. So AC, DC. Now, let's talk through that, and we can talk about how the order and how you apply it to your systems. Let's start with async. So with async, now we're not talking about async await here in .NET or TypeScript or one of these things. That actually is very much not this. That's a whole other thing, and I really wish they'd named it something else, but that ship sailed, and here we are. No, here we're talking about is decoupling things so that the performance critical path that has to happen in that like 5 requests per second, 100 millisecond response time, we do the least amount of possible work in that critical path. And this is one of the first places I see most dev teams shoot themselves in the foot, is they look at the business requirements for handling a certain request, like user signs up and they hit the sign up page. It's like, well, business says you need to do these 8 things when they sign up. All these 8 things. Well, if we do them all literally in order, like, okay, they got to prove that their login is right. Yep, we got to do this thing. Oh, yep. We got to send them an email thanking them for joining our site. We have to go through and tell sales that the new customer has joined the site. We need to show them our GDPR compliance information, And all these steps, you add them all as synchronous elements in that workflow. It's not that any one of them necessarily is slow. It's that the join of all of them, the union of all of them, is slow. So we want to decouple that stuff as much as we can. And the first technique to look at there is the idea of queuing work that can be completed later somewhere else out of that critical path. So imagine, for example, that when they go and whatever the work core step is, like, okay, we need to we need to let them sign up and log in. You have a bunch of things you need to do. You want to email them, do all these other steps. Sure. But let them log into the site and get going. You can email them their welcome packet, telemarketing, do other things after that. In fact, the system I just worked on, we literally deferred creating almost all the account infrastructure and everything until after they completed their login, because we realized they would, until they completed a purchase, like got into the site, picked a product, went to the purchase cart, and got through the payment gate. Till they got to that point, we didn't need them to exist in the back-end systems. There's no way to get through that. There's no way to get through that in less than like a minute. So we had plenty of time to get it handled in the background. And in fact, what we could do was, if they got to that point and we hadn't created them yet, we could say, sorry for a minute, we need to complete setting up your account, or do something like that, which no one was ever going to see. You can't, in terms of figuring out the critical path of this, it really, like what we're talking about as a starting point here for simple web requests is, if you're looking at a given, part of your API surface area request or action user can take, going through the sequence of the business operations and saying, which of these operations must complete for us to correctly execute the request the user has made. So in other words, if the user is signed up so that they can access to your website, what you need to do is give them access to the website. You don't need to actually couple that back to, and we sent them the welcome email and done this and done this and done that. Now, it's the simplest way to code it is to do all those things, but we don't have to do those things. So as a first pass, in fact, one of the most useful things I've seen with customers is, like, go through, when you have long running operations, to look at that and say, well, wait a minute, can we, like, let's move these things that take a while, move them out of the core, synchronous flow, and instead queue them happens behind the scenes asynchronously. I will say I've got pushback on some dev teams because it may make testing more complicated. It may make coded tests, unit tests, integration tests, that type of thing more complicated. And I have a little sympathy for that, but not a ton, because the difference it can make to your site's performance is massive. And the aspect of it smoothing out load is also great. An intrepid observer, when I previously said, well, hey, Meyer only needs to worry about 4.4 requests per second, is going to point out that load is not uniform across the day. I will bet that a bunch of, for example, Meyer probably gets a ton of load right before work, during lunch hour, right after work, when people are quickly going to figure out, do you have this thing that I want to go and get, for groceries or what have you. And a lot of times we do have those hot moments in our load paths. So those pages that are part of that hot moment, we need to optimize, particularly because we know we're going to get surges in that. And if we can take this work of like sending out the emails and doing other background operations out of the synchronous part of the process and instead let it happen in the queue, it's shocking how much scale you can get even with very minor amounts of decoupling there. Because if the problem you get with web server performance is, for example, if it starts getting behind, you're not just losing, it's not just the slow request that gets delayed, very quickly that cascades into even fast requests getting delayed because they're waiting in a queue to get to the web server itself. So that's where this has a real knock-on effect in terms of overall site performance that is not obvious, even if you're using a very, like if you have relatively short latency in the queue of work that you're doing, that you're putting off, because you're keeping it from causing a backup farther upstream. So it's really pretty impressive what this can do. And once you tell the dev team, look, we have queuing infrastructure, it's readily available, let's use it, and look at each of these interactive, particularly end user interactive requests. If you can't guarantee it's going to complete inside the threshold of our performance guideline, break it up and figure out what part of it absolutely has to be completed to tell the user it's handled versus the actual completion of the execution of it. So I'll give you another example of this would be when you go and order something, when a user clicks, if you think about it, when a user completes their order, what do they really, really care about? And we'll talk a bit more about that later, but we tend to put way too much into like, well, we want to guarantee that all these things have happened so that there's no possibility could ever fail at that point. And we really don't need to make that guarantee. And instead, letting it be fast to the user is what matters. And we'll talk about how you can do that in a responsible, practical way a little later. So another asynchronous technique is not to take the work the user requested, so those on request defer work. That's one standard of async. But another example is do work before it's requested, speculative execution. So an example of speculative execution can be pre-calculating and pre-filling out caches or things like that before the user requests it. You could imagine, for example, is simple on one hand of static site generators are an example of speculative execution. So I use Jekyll to run my portfolio site and the Loop company sites and things like that. And what it does is when we make a change and it builds up the site, it generates every possible page the user could request as HTML files. It has no idea anyone's going to ever read those requests, but it generates them all at build time. And then when someone goes to view the site, that page already now is calculated and exists. I essentially converted everything from dynamic requests to static requests. But we don't know that anyone's ever going to request that particular page between when we generate the site and next time we generate the site. So we're speculatively doing that work ahead of time because that lets us burn almost as long as we want to build the site, but the viewing of the site will be very, very fast. This is a great technique for things where particularly if the number is just too big to do on demand. And I'll give you a good example of that. I was working with an insurance company, and the problem they had was producing commission reports. Now, salespeople, absolutely, the minute they knew, like this day of the month, 2 days before I get my pay, the commission report's available, and I can find out what I'm going to get across all my things. And all of the salespeople in the US would go into the system in the space of like 3 hours and grab their commissions report. And they hated how slow it was. The system needed maybe a couple of minutes to produce a commission report, but when you had 10,000 salespeople, and these are independent insurance agents, all requesting their commission report, it would be hours and hours of backlog across the system. And they'd spent a lot of money in engineering trying to get those time down. Like surely they said we can get it down to, we can generate these commission reports in 30 seconds or less. And they just couldn't get to a number that would actually give them the scale. So I went back and asked them a different question when I was looking at the problem. They brought me in because we have an expertise in the SQL databases. And I looked at it and said, you know they're going to ask for it. High odds are going to ask for this report. There's only 20,000 possible salespeople in the US. What if the night the data closes out, after it closes out, we simply generate 100% of those reports ahead of time? How long would that take? And the answer turned out to be about 2 hours. If you just did them, in kind of an optimized, steady flow, you could do it in about 2 hours, do all the reports, 2 to 3 hours, do all the reports. Particularly if it wasn't having to fight in the database against the traffic of the day. So I was like, let's just generate them all. Let's just generate them all in the middle of the night, in the dark, when no one's looking. And then that way, when they come and get them, we just check the file exists. If it does, we just display it to them. It was by far the lowest cost, most straightforward way to fix that problem from the standpoint of the user. Now, we don't know that the customer's going to come, the salesperson's going to come pull that report, but it was worth speculatively executing it ahead of time just in case, so we were ready to go. And this idea of using scheduled requests like nightly processes is not an uncommon way of, again, shifting things into that async domain. So you can do them not when they have to be done, not when they are time critical, but when you have luxurious amounts of time and can do them so that they are ready to go when it's needed. All right, so that's a quick spin around the async aspect of how we scale applications. Let's talk about caching, the C. So what is caching? Fundamentally, we're saving the results of earlier work nearby where they're handy to use again later. And this technique is just used all throughout computing. I don't think we use it enough in our systems and software. It's gotten better. But I remember 5-7 years ago having to fight with people to do any output caching on their web apps because they were so worried about what it might mean to do. So we want to save those results of earlier work where they could be reused, and then we want to apply a cache in front of anything that's time consuming. You could almost imagine it's sort of like if you have something that's working here and that's upstream, you want to have a cache of stuff right here for it because it's always then work to go upstream and get it. And then on the other side of that, whoever you're calling, they need to have a cache for what's upstream of them. So caching, you can apply it over and over as a pattern, which is great. And it is, there's no way to make a request faster than never having to redo it, right? The whole point of caching is because we're reusing work that was done before, we're literally not going to process the request upstream. And that, again, has a cascading benefit because not only is my request fast, but I didn't make a request of the infrastructure to do it. So I've left infrastructure capacity lying around for the non-cache requests to go after. So very powerful technique. What's a little counterintuitive, and I say that because earlier in my career, we tended to do this the other way around. And actually in .NET, I think we tend to do this the wrong way around a lot. But caching, in my experience, is actually easiest to apply from the left to the right. If you think about the user or the requester of the process being on the left, and the right being your permanent data stores, ultimately as you go through the system, it's actually generally easier to apply where you need it, see the results, and get great effectiveness out of it if you take from the left. And the reason is that if you start adding caching from the left, you're eliminating requests from being seen by the items on the right. So you get that scale up benefit, and you're responding the fastest possible because it's never having to process that request at all. What's interesting particularly about this, where again as developers, I think our intuition missells us on this, is that simple caching strategies can be shockingly effective. Early on, and there was a big kind of argument between when any framework was first coming on the scene, between it and the Hibernate crowd coming out of Java. And the reasoning is that the Hibernate has extremely elaborate algorithms for cache invalidation and process. So it's this Mondo ORM for Java, very smart, extremely smart actually. And that was their idea. Each term was be smarter. And so they were really driving to get those cache hit rates as high as they could. And they made it very, very clever. One of the biggest things they would do is like if you did an update, it would figure out exactly what elements of the cache it had to invalidate to handle that. When any framework 4 through 6 shipped, their internal caching that they introduced initially was really simple. Dump everything on update. And if you think about it, this is still based the way the EF context works. If you don't want to have what you have in RAM, just dump it and start from cold. And that seems outrageous. Like, you mean every single time I update a record, I just lose, I suddenly get 100% misses on my cache. But here's the interesting thing about that. The flows we use as developers and the flows our users use are nowhere similar. As developers, we tend to focus all of our time when we're interacting with the app on doing things that mutate state and doing them, like do them once. Because we're not using the app as a customer, we're using the app as a developer testing a feature. So it's like, all right, I fired up the application. I go into the user profile page, I modify the last name, I hit save, and I go back to the home page and confirm that the last name was changed. So we tend to be very modification heavy because that's where the dev effort is and that's where the bugs are. But in real use, reads, outnumber writes somewhere between, depending on the system, 10 to 1 and 1,000 to 1. I mean, it's just compelling reads outnumber writes. And that means even if you ditch everything on a write, you will rapidly refill that cache and then get huge benefits from it. So really simple cache strategies for validation can still have shocking benefits in actual real world performance. Really short caches can also have shocking benefits. I've seen systems where we literally introduced a 15-second blanket cache on output and chopped load by 60, 70% on the system for no apparent impairment of functionality. So caching can be hard to sell because developers, caching fundamentally means that we've opened a consistency potential problem, right? Where the stored data may be different than what we're returning. And we're very uncomfortable with that. I mean, how our test is going to handle it and things like that. But from a sheer, it performs under load, it's the most amazing tool to get up to real scale. Because the other thing about caching is even if you do a very short cache, let's say you do a 10-second cache, and now I 5x your load, well, it's almost all coming out of cache. So who cares? As you know, even with a very short cache, very short caching, still the hit rates go up and up as your load goes up. So your benefit escalates as the general load increases. I'm going to pound the caching a little more. When I started in the industry, we literally sat back and thought about, like, how do we load the whole database into RAM? Well, you cannot load the world. You can't. But apps ask a lot of repeating questions over and over. If you actually look at the volume of traffic to your system, it does it a lot. I'll give you an example with Loop. So Loop is an application telemetry product. So it's a centralized logging system. And centralizing meaning your app's running everywhere, can upload data to Loop. So it's very write heavy from that standpoint. But by something like 5x, the number one request the Loop API gets is to get the configuration of a given repository from the server, so it knows whether it should upload its data or not, and is the server available and what version is it. That single request, the config get, is like 5 to 10x every other API request. So we cache that to a crazy degree, to the point where it's so that it never even hits the servers for those repositories. It eliminates the vast majority of the requests actually coming up to the cluster. And that's because these answers in computer changes do not change often. So we might think about, even if I had a banking application, you might think like, well, someone's going in and looking at their bank statement or looking at their transactions online, like this data is changing constantly. But it really isn't, again, in computer terms. Often change would be like many, many times a second in computer terms. In human terms, once a minute, you could then cache it for 30 seconds. Because authority of information is very expensive, and we don't generally need it. This is where I think also our tendency of how we develop systems for good engineering reasons can again lead us astray. Let's say that you're developing an application and you know for certain parts of it you really do need a relational database with transactional support. Absolutely. I've built a bunch of those applications. But now once your app has that, well, we've got a SQL database here and we've got this, and here's our main application. Well, we need to store this information as well. We might as well store it in there while we're at it. Oh yeah, and here's the user's profile page. Well, let's just go ahead and put that in the database. And so the user profile, it's got their, their first name, last name, email address, blah, 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 all this stuff about it. The thing of it is, when we're storing something in a transactional data store, and I'm not picking on SQL, actually, it's an amazing product. You could say the same thing about Mongo or Cosmos, for example. But when we're storing it into a database data store, the effort to actually go back and get it, it doesn't really know if you don't that much care about how fast this data is maintained, or you really do. It's treating all of them as if they're the same. So it treats the rate at which the integrity of my last name is in the same par as my bank balance and the nuclear launch codes. So when if I just kind of do a straightforward implementation of my app of like, oh, I want to show, hi, Kendall, in the upper right corner of the application, when it renders the server-side content of that HTML page. And it goes off to the profile. You have a profile provider, which is nice and injected in your context, and it goes off. What's it do? Well, it goes off to grab it from the database. So it's going through the whole process of, I need to talk to the database. Let me authenticate to the database. Let me connect to the database. Let me ask that database, which is for sure running on another platform, probably behind a load balancer, to give me this information. That database, it doesn't just hand you that information, that last name. No. It's going out and it's confirming that what is the exact transactionally accurate value of that last name, potentially all the way down to persistent storage to guarantee that there was not 1 millisecond before transacted change to that last name value or first name value to then return it. Because it doesn't know you don't really care that much for it. So it's going to treat it the same as your bank balance or the last key used on a table or what have you. So does all that work to come back with a value? But the reality of it is, if you step back from as a user, let's say that I went to the site and it said, hi, Kendall. And then I went to the profile page and said, actually, I go by Ken now. And so I changed my first name to Ken, hit save. If I go back to the home page, it still says, hi, Kendall. I'm not opening a bug report. I'm not getting upset about it. I'm just thinking like, oh yeah, it'll update in a minute. And in fact, as long as data changes move forward, users are really tolerant of latency. When I say tolerant of like minutes even for that stuff to update, as long as they don't see it go backwards in time. Imagine another test for yourself. You have your banking app up on your phone. You go to a Starbucks, you get in line, you order a coffee, you hand them the card. $12 for your coffee later, you're now waiting for the coffee to show up, and you're hitting refresh on that mobile app, waiting to see that transaction show up. You're really actually okay with that transaction not showing up by the time you've received the coffee, drunk the coffee, and are walking out of the store, as long as once the transaction does show up, it doesn't go away. And that's straightforward to deal with in systems terms. So I mention all of this because our engineering tends to get in the way of us doing a great job of that. So yeah, Stephen, that's a great point. Setting expectations with the user of how it's updating, how fast, can get you out of a world of trouble. And let me just hit that point for a second, because again, as engineers, we tend to want to fix things the hard way because that's fun. I just want to make the system faster. We'll get a bigger database. We'll do all of this. We'll have it so it's light speed to get that value change. We'll use a WebSocket to talk to the server so that you can literally see the keystrokes of someone changing the first name as they do it. It updates it in the right-hand corner. So they go, no, you don't need to do that. Talk to your business, talk about what the customer values, and then design the UI to avoid the problem in the first place. So much better use that way you're putting your performance work into the place that matters. All right, so you talked about caching. A and C, we're on to D, distribution. I list this last for a reason. It's the technique we tend to go to first, but it's actually a bad technique to go to. So distribution is distributing requests across multiple systems to get handled. And this is our classic like web server scale out, right? So this is, I just have more web servers. Now we'll load balance across them. I'll go into, Azure App Services and tell it to scale out to X nodes, etc. And we'll distribute the work, and that's how I get faster. But this should nag you, because remember we started with Meyer only needs 4.4 requests per second. Surely a single core Raspberry Pi should be able to handle that. So if you need to scale by adding a bunch more cores, that should be setting off a little bit of an alarm bell in the back of your head. Now notice, by the way, I'm talking about scaling here. I'm not talking about availability or disaster recovery. There are reasons to have multiple systems for that. Not the subject we're getting into at this point. We'll talk a little bit about it at the end. So when you're doing distribution, a key thought here is the less state that you're holding in the middle, the easier it is to distribute work. So whatever the layer is that you're trying to distribute, it really needs to have either stateless or as close to that as you can make it to make distribution effective. And otherwise, it's that classic consistency problem that poses us. Because if it's holding a lot of state and you start distributing it, we have to keep that state consistent across all those nodes. If on the other hand, like they're not holding any state, then we have nothing to keep consistent, and it's easy to apply distribution as an approach. This is why at the end of the day, distributed databases are hard, almost unsolvable in the true sense. If you look at the way that they actually solve distributed databases, they're either making selective compromises on consistency, or they're not really distributing it. They're just breaking it up like by data partition area so that they can have multiple servers, but only one server could handle a particular request. It's just the body of all servers can be distributed across more than one, or if all requests can go across multiple servers. So distributed database is very hard. Distributed static content server, very easy. And that's why we're not even worrying about that element when we talk about making like our system scalable. Because static content, we don't have a consistency issue. Like that's a very solved problem. So now doing distribution and request routing for availability purposes and other clever things like that, totally different phenomena. Not really drilling into that at this point. Availability is another angle to look at your architecture from. All right, so we've hit A, C, and D, async, caching, distribution. But in the end, what kills our app from scaling, the reason we struggle sometimes to get to that 4.4 requests per second is consistency. Consistency is the degree to which all parties observe the same state of the system at the same time. And that, the more we require that, and imagine, for example, again, like say, let's talk about your balance on your Starbucks card. If it has to be absolutely consistent between your mobile phone, the core systems inside of Starbucks, and the POS system at the store, that's a very hard engineering problem. And in the end of the day, you're going to have to compromise some degree of absolute ruthless consistency to scale beyond small numbers, right? You could scale actually, like if you could fit yourself into a single SQL database, a single web server process, and then customers calling it, you can actually have very few scalability consistency compromises as long as you fit inside that box. And this is what we were doing in the 90s. But that's it. Like you've got a hard wall at a small number of requests and you can't go beyond. You're gonna have to start compromising on consistency. So it's just fundamentally really expensive. But the cool part is the real world just doesn't require us to have that level of consistency we tend to demand. We can get around it a lot. And that opens up the doors then to async. So async, an example that would be like you go and you actually, again, the Starbucks thing, you go and you actually order the coffee, but it doesn't actually change the final balance on your internal record of your card until, for 60 seconds in the processing from the queue back at headquarters. That's fine. From a business process, you can make that work. And that significantly, although it's technically consistency degradation, it is a significant improvement in scalability and performance for the whole platform. So let's talk about some common consistency challenges when we engineer into our systems that we can, that are sort of hotspots we should look for and then work around. One of the first ones are singleton data structures. So when you make something like, say, order numbers, they have to be monotonically increasing. You are creating a global consistency problem for the rest of, for that whole platform. I've had a number of these cases. Oh my Lord, accounting people love to say like all the invoices or order numbers, they must be monotonically increasing with no gaps. Well, that's a pretty hardcore consistency guarantee. It comes down to essentially like we have a store procedure and a table in a database, and you have to go to it and you have to request an order number, and you can't actually, you have to make sure your order is going to commit all the way before we can grant the next one, because if not, it's going to get that order number because we can't have a gap, blah, blah, blah. These structures really hurt your overall consistency. I love challenging sacred cows, and I love it when I run a new system and I find a scalability problem like they're doing monotonic invoice or order numbers, and they're a high scale business. I basically, because you'll notice, for example, Amazon doesn't do this. You go to order something from Amazon, you don't get your order number 1200 and blah blah, your 12 million blah 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 blah, you get what a GUID with some other modifiers on it. And there's a really good competitive reason for this. So if you need a good way to talk your business out of this one when they're really attached to it, point this out. If you're in a competitive industry, I was working with a distributor in the Midwest recently and pointed this out to them. If I wanted to know their volume, what I would do is every Monday morning, I would go and order a 25-cent part to get myself an order number. And I would look at what the gap is between those order numbers over the course of a year. And so for 25 cents plus shipping, I'm getting a massive amount of business intelligence into the volume of my competitor, because you're leaking, it's information leakage happening because of the way the order number data structure is happening. So if you can't convince them on scalability terms, see if you can do it on security or corporate, or competitive terms. So another consistency challenge we do is when we're holding state between the endpoints of a process. So this scenario happens where we are, yeah, it's totally a side channel tech, absolutely, and yep, people love to create these. They love to give data meaning. A little digression there for a second. One of my rules of systems design is never show an end user the actual keys to the values, because any value you show them, they'll want to make it meaningful. Humans are desperate to make values meaningful. And so I often use, in a lot of our systems, we basically use GUIDs as the one true key for a lot of reasons, but then we will create what we call a name field that will be like a 10-character string name. And then when they come back and say, well, we want to make sure that all orders start with ORD value, I'm like, fine, no problem. ORD, then random value. Because now it's meaningful. They can look at the thing and know that's an order. But never show the actual keys to an outsider, to a user of the system, because they'll try to make them meaningful. So state held between endpoints of a process. So if you have a mobile app and you have a data store and you're holding state in the middle, you're creating a consistency challenge, because it means things like you tend to have to keep routing requests to it to handle something, because it's the thing that has that middle ground state. Maybe it's the thing in flight processing the item, or it's the only one that can access, that has certain data. It's merging between multiple endpoints. But if it's the degree to which you end up grouping those items together and holding that state, a good example of this, server-side session state. We used to have this problem all the time in ASP.NET. You used to have all this problem where people would load this stuff up into session state. They wouldn't think about the fact that this is now on that server in RAM. So users doesn't have to be logged in. They're fundamentally coupled to the session state on that one server. So now we have to route that user back to that server to complete their requests. And then we create a consistency challenge for problems. And it will ultimately hurt our scale. This one's a little more obtuse, so let me explain it. So the degree to which you have to have consistent results for queries across partition data sets. So an example would be, let's say that example would be like looking at data from the two different ways. So like you're looking at, say, order revenue by looking at the ordering system, and then also looking at it from the accounting system. Because, hey, if we actually ordered this and booked it and the order completed, well, then it should show up as revenue over here, for example. And these are partitioned data sets. They're almost for sure separate systems. And the degree to which you need to make sure that they're absolutely guaranteed consistent at any one moment in time, you end up creating a lot of scalability challenges between the two of them, because they have to constantly be pushing and synchronizing data instead of doing it, say, in a daily catch-up feed. And I mention all of these because, in particular, this last one, I've seen people pretzel their platform to make sure every aspect of the system update at the same moment. It made it very testable, made it easy to pass their user stories and acceptance testing, but it killed their scalability with big transactions and things like that, trying to update data stores. And instead, if we sat back and looked at it from the real business standpoint, we didn't need to do that. The company I just exited, one of the things we did for performance that really improved things is we started using Elasticsearch essentially the full free search engine for data where the system of record was a SQL database. It did mean it was behind, but the reality is the rate of change in the data and how it applied to search was such that the fact that we could provide answers so fast, it didn't really actually impair the results to the end customer. Because although data was changing, the data they were searching on was not changing that fast. And so we were able to let those two be a bit apart. Now they were normal day, they're seconds apart. Worst case, they could be an hour apart. Theoretical worst case, because we didn't hard couple them. But we even at that point realized, no, people will be fine with it. So for example, if they updated the person assigned to the case and they were searching by that person and didn't show up, they go, oh, let me search by the previous person. Oh, yep, there it is. People are actually very adaptable. You don't have to solve every corner case, particularly if you can get a huge performance benefit or scale cost benefit by not doing it. All right, we've talked through all the basic theoreticals. We've talked through the idea of async, caching, and distributions, giving you more scale, and how consistency stops you from being able to scale. So let's walk through your application. Fortunately, I got an architecture diagram of your app right here. So what's going on in this kind of thing? Where are we creating consistency and challenges in the typical app? There's some stuff we don't even think about, like when you're talking to if you're talking straight from a browser to a web server, for example, there's session state, which we mentioned, but also SSL is itself a point-to-point encrypted connection. If you're not terminating it at a load balancer and then not doing SSL upstream, there is state held in those connections that have to be between those two endpoints. You can create interesting coupling. Customer I was working with in the Midwest recently had this problem where they were allocating so much RAM that the garbage collector delays created significant coupling for requests hitting the same server. And that created coupling and challenges they didn't expect. You can run out of network sockets. You can have an excessive request queue going into the web server. That means that like 10 slow requests can end up stopping all the fast requests from working. So all of that's happening even there without it being in your code. Go to the database level, well, transactional isolation, you start isolating updates from each other. If you're doing other reader-writer locks, those singleton data structures we talked about where you hold it open for long periods of time, all of those can create significant consistency challenges that prevent the scaling of that item. And it's not the product's fault. It's the philosophy or architecture you use and how you approach the product. So how do we fix this? Well, we're going to apply things in an order. I'm going to walk through and show you kind of how you can stage through these things to get a consistent result. The great news of what I'm going to show you is it's an iterative pattern. So in other words, if you gave me a system and said, Kendall, we are here, we need to get to there, I'm going to go through this pattern step by step. And if at the end of it, I'm not fast enough, I'm not scaling, I'm going to go back to the beginning and start again, because I'll open up new opportunities for myself to do the iteration again. Okay, so where do we start? First step is caching. You probably saw this one coming, because we can eliminate requests that we never had to do the work in the first place. We get this massive knock-on benefit. There's already caching going on. So if you think about 100%, starting at the true logical engine of the web browser itself, the web rendering engine, and the request it thinks it's executing. Let's take that as our 100%. Well, right off the bat, the browser itself does caching. Now I know you're a developer, right? So your relation to browser cache is, it's that thing I'm defeating all the time to do my testing, but it's your biggest friend from deployment. Now let's be generous to this model and say that we only managed to get a 50% hit rate of browser cache. It's, by the way, dramatically better than that, but let's just pretend we only get 50%. So cool, we've eliminated half the requests right there. Now what's happening on the server? Well, if you've enabled it, even for a dynamic request, it's not there by default, is output cache. This is where we talk about adding it from the left to the right, but think about this. Let's say, for example, you have an Angular app and a web API. The reality is, for a ton of your requests, what's asking, like, give me the JSON response of the list of all blah, blah, blah for this. Can't you cache that data for 15 or 30 seconds? You probably can. And still have your app behave in a correct, always moving forward manner that will, from the standpoint of the browser, function correctly. Output cache can eliminate a huge number of requests. Depending on whether you're doing server-side rendering or not, you get different rates, but it is absolutely typical to get over 80% hit rates on those, even for dynamic pages, on output cache on a system as it scales up. Of course, in testing, you're not hitting this because you're doing you're varying stuff all over the place. But in the real world, people hit the dominant pages, they hit the entrance point pages, and if those have dynamic requests, you get massive benefit from that caching and that cache hit rate. But we're not done. We can have a content cache. So before your web server waltzes off anything out of its process, to go get it, or even in its process, it can be calculated values that's derived before. You can have that in-memory content cache, and this is where, again, every framework has some sort of library for in-memory cache management of in-flight objects. Be sure you're aging things out, but I mean, so it's not a permanent memory leak, but you can get tremendous benefits there. And again, it's not unreasonable to get 80% plus hit rates out of that kind of thing, or higher. And if you get, so a 90% hit rate, that actually is, for most systems, if you're really doing caching at that level, you can get to that 80-90% hit rate before you actually have to go back to true storage for the true volatile changing value. And once you've knocked it down to like 1% of the original requests. And we're not even quite done, because then even this, of course, if you're using a true database product, it's going to have its own set of caching that it does. It's going to have its own in-memory cache pages and the rest of it. Databases get most of their performance by caching. They're very clever cache engines at the end of the day. Now, something like Redis literally are that, but that's true of any of the relational databases. They came, or even document databases. They're trying not to hit disk, because even in the age of SSDs, disk is far slower than RAM and far slower than not having to calculate it in the first place. We tend to, as developers, argue against cache, because when we're doing our coding and our running our unit tests and our integration tests and things like that, cache can make it appear that there are bugs that aren't there in the real world, or you don't get the benefit of it, because we do things in a very, I do this one path through thing. Yes, it is correct, and now I'm out. We don't see the benefit of it. We don't get the hit rates, but your deployed application will. Okay. So we've applied caching. Now let's do some distribution. So notice we went caching first. We didn't just go to the distribution first. We went to caching first. So you got a whole, one thing to keep in mind, by the way, is that there's already distribution going on, which is the more work you stuff into the browser, the more you're doing distribution from the get-go. Because if I go and have my browser, it's calling into some sort of reverse process, your load balancer, which then is splitting work out to your back end. There are way more of those browser instances than there are my web server instances. So the first most simplified form of distribution in a web app, at least, is what can you have run in the client instead of running in your server? There is the cumulative horsepower of the browsers will always exceed the horsepower of the server for any number of more than 10 clients. It's going to absolutely exceed that. So, okay. Now, we still have to do some things. We got to be careful here, because we do not want to throw in a bunch of state into this distribution tier. So we got to worry about session state. We have to worry about identity management, make sure that we can correctly reprocess your authentication. Now, you can get around some of this by doing sticky sessions from the get-go. So sticky session would be a given client talks to a given backend as long as that backend stays available. There's some pretty reasonable reasons to do that, even in fairly scalable systems, because you're actually going to improve the hit rate of your caching, what we just talked about, if you tend to send the same people to the same backends. So sticky session is not inherently a bad idea. And I know, like on Azure, Lou says, hey, turn this off to improve the scalability of your system. And it is improving scalability in one sense, but not others, which is to say that, again, imagine if I'm a client, I tend to burst requests. Like, I'm going to go into my account, and then I'll look at this, and look at that. And let me go back to my account. Let me go in, let me go out. Let me go in, let me go out. For dynamic pages, I tend to have a burst of activity around a corpus of data. If I'm routed to the same server, there's a far higher probability that that's all still in cache, like this content cache, things like that, still have that content when I get to it. So you can still gain something from that, but you don't want to depend on it. You want the user to get an error if they get bounced to another server. So you need to make sure that authentication and other things like that are factors, so the software will still work if you route them to another node arbitrarily. But you can often get a performance benefit by actually consistently routing them to the same node. And that's our basics of distribution. Now it gets a little bit bigger. Let's say that our problem's not at the web tier. So we have our client web browser, and our problem is actually at the storage tier, which is more often than not the case, right? Because if our middle tier is stateless, we really shouldn't be in a world where it's the dominant aspect of our performance. We probably are having multiple for redundancy purposes and other maybe continuous deployment reasons, things like that, but not for performance reasons. So if that's the case, where are we really bottlenecking? Almost for sure, ultimately back into the storage area. And that's where the strategy of partition storage zones come into play. And this is a technique that's almost ubiquitous in document database systems, but you can do it absolutely in relational systems pretty straightforwardly. So we do this in Loop, for example, where what we actually do is, as a first pass, is we separate the official data store by customer. So we have a relational database that supports key data behind each Loop customer. Every customer's repository, I should say, every customer repository is a database, and it lives somewhere. There's only one of them. They're never distributed, but we're partitioned by that. And that means that if as long as we have activity distributed across customers, they're hitting different backend storage blocks because they're hitting different physical databases in the backend. So customer B goes that way, customer A goes that way, and even if we could be doing it by splitting the servers apart, we could even do this with these are all the same web servers and talking to multiple databases and partitioning at that level. So you can do the same distribution tick. We didn't think of it just in the web server tier because they're stateless, which makes it easy. To do it in the storage tier, you pretty much have to follow a partitioning strategy. Because remember, distributed database is hard, but partition it, now it's not a distributed database. It's just a field, it's a collection of databases. And the most straightforward way you usually do that from a development standpoint is literally you pick a key criteria like a tenant ID or a repository ID or some core characteristic, and then literally have the same schemas, but just completely separate corpuses of data in each of them. Now, this has created consistency risk, right? Because now let's say that I want to run a query to find out how many, for Loop, it would be like, how many gigabytes of log data have we received today? I'd have to query each of these databases. And my answer would then be a not exact instantaneous snapshot in time because I'm querying hundreds of databases and aggregating the results. So it's not going to be exactly like literally exactly on the dot at this moment in time, this was the result. But the reality is I don't care. I don't need it to be precisely at the spot at this time that was the result. I'm asking the question more or less to just compare activity day to day. We can be off by minutes, even half an hour, and it doesn't change the utility of the data. So we'll compromise in consistency, but it doesn't really impair the actual business value of what we're doing. And the scalability gain is massive. This is how, early on, this is how Hotmail worked. As long as any one mailbox always had to be able to fit within a server, your mailbox lived on a server. They set up a ton of physical servers, virtual servers eventually, to host people's mailbox, and they were able to provide Hotmail mail to people easily. Partitioning databases it's just a great strategy to give you really high scale, and it's other advantages. One of the other reasons I love this, I've done a lot of SaaS platforms that are multi-tenant. I really like partitioning data by tenant because it also matches the life cycle of the data. In other words, the tenant comes in, we create them. They have their own block. If at some point they will leave us, maybe in the distant future, but at some point between here and the heat death of the universe, they will leave us. And when they do, I can go reclaim all that space by simply freeing their storage partitions and deleting them, which is a very cheap operation to do in virtually any system. I can also, if they called me up and said, oh my God, something horrifying happened, we need you to roll us back, I can do that as well to a point in time because they are partitioned off from everything else. But let's say that this doesn't get you far enough. You've tried this technique, right? So you've started off, got multiple browsers going on, we got caching going on, but we're still outrunning, maybe you have a particular customer, there's just too much going on, their database is getting overwhelmed. I can't afford to buy a big enough virtual server or whatever to run them, and now I'm looking at very expensive options. Now what do I do? Okay, cool. Let's talk about partitioning storage within a zone. So with this idea, what's happening is that you now you apply it essentially within the tenant characteristic. So instead of being a collection of identical data stores in terms of their capabilities, partitioned by a top level characteristic like customer ID, instead of doing that, we actually start splitting it down where it is, okay, by types of data, we're going to break them into their own data stores so we can bring capacity by these sub partitions. So for example, all right, I'm going to break down my application. So I've got my order database, the products database, and the inventory database. And instead of having them all in one database for that tenant, I'm going to separate their orders, their products, and their inventory into multiple databases so that I can now bring 3 times, if you will, the horsepower to the table. But this has some other benefits that are not obvious. This gets into a bit of the domain-driven design paradigms and some of those kind of characteristics. But if you sit back and think through the ecosystem of your product and the different domains of the data, like orders, products, and inventory, you'll probably start to realize things like, well, wait a minute, these have different characteristics of the rate of update, the rate of change, and the read to write ratios. And so by separating them into the separate databases, you actually start getting better cache, for example, hit rates, because you don't have one noisy problem crowding out other things, for example, because they each have their own resources. But you also can start doing things, the better thing I love, particularly today, where it's so much easier now to bring more platforms, more infrastructure as a service to the party, is you might split it. Let's say it's all started off as SQL because some of the things really wanted to be a relational database. And then you start splitting it like this. And you initially say, fine, we'll make 3 SQL databases, and we'll just take the same schema, we're going to split it apart, and that's okay because updates are only happening within any particular business process. Updates only happens really within one of them, so I don't have to worry about distributed transactions or any of that malarkey, and we're all set. But then you sit back and realize that, you know what, products really doesn't want to be a relational database. Products wants to be a document database because of there's a better impedance match with what I need to store for the product data, its update life cycle, and things like that just align better with the characteristics of a document database. So you know what, now that I've separated it apart, it doesn't have to be a SQL database. I can make just that bit a document database. Or in fact, like maybe it's not even a database at all. Maybe it is a stack of JSON files in Amazon S3 buckets, where you literally do the search by just looking for the resource ID, and if it's there, boom, there's your JSON data. And now it's crazy cheap and scalable, which is wonderful because of all these things, we hit products 100 times more often than we hit orders and inventory. So it opens up an additional set of flexibility if you really get to the point where you need this scale. Now, I'm going to stop for a second, back up, because what I don't want somebody here who watches this talk is, oh, I want to have my app go scale. So what I need to do is have a SQL database and a document database and just straight up file storage and in the cloud somewhere so that I can partition by all these characteristics. No, stop it. If you do not need the scale, do not do this engineering. This is not nothing to do. This is going to have operational cost. It's going to have it's going to be a consistent load on your dev team to manage multiple storage systems, multiple technologies and clients. There's inevitably some messiness around the edge of these things. It will cost money. It will cost time. Don't do it if you don't have the problem. But if you have the problem, yes, here you are. Okay, we start with caching. We've done distribution at each tier. So that leaves us with async. And I had that one last. And the reason I had that one last is it's usually, one, the most challenged to get teams to adopt successfully. And two, you need to do it benefits from the work you just did at these other things where we sort of unkinked some of the state and those items to really be able to gauge async. I love it. I could use it maybe a little earlier than I need to true async, but but I would take a quick pass. Like I would go and add caching. I would look a little bit at distribution to see if it solves my problem. And if it doesn't, well, let's take the example I start off with of the web request where it's like, hey, I got to send an email, do all these things. You're not getting that done with distribution. You're not getting that done with caching. So now we've followed async as the way we solve that problem. So how do we do that? Well, fundamentally, to do something asynchronous, we're going to have a place where we can persistently store things that we can trust. Because if you think about what happens, let's say I'm ordering something. As a user, what's the covenant I'm expecting from the system? I'm expecting that if I go through, so, you know, I like, there's a regional Mexican chain here called Baja Fresh. I love their food. My wife and I are huge online orderers. We'll order it online, we'll run down and pick it up and boom, bring it back home. For me, I go through and I assemble my whole order and then I click, I click the button to say order. The guarantee I'm expecting, the covenant I'm making with the system is that if that comes back and gives me a thumbs up, then that order will happen. I don't need to guarantee that it has happened. I just need to guarantee that it will happen. So that, in other words, there's nothing more I need to do to make sure that that happens. So that actually could have gotten to the point where it just literally said like, yep, your order is structurally valid and I'm putting it in the queue and I'm returning to you thumbs up. It didn't actually have to go and do all the pieces, get the order, the store, all of those items to make that happen. As long as for any failure, you've got a compensation mechanism. We'll talk a little bit more about that in a minute. But we tend to think of it as being the whole thing because from a development standpoint, we have to do all of that work. But from the end user's covenant, when they click order, what does it really mean? Well, it means that once that thing comes back, I could turn off my phone. There's nothing more I need to do. You have the order. So as long as you have a persistent queue and it has the order, you have the order. Real queue systems like Service Bus and the like, they have dead letter queue spots. So even if a message can be processed, it doesn't just disappear. It goes somewhere where your system can then take an action to handle it. But in this straightforward case, it's going to happen virtually all the time. You're going to put the order in the queue. Having done that, you have some order processing server, serverless function, something, monitoring that queue, picking it up, and going off and doing the work. And maybe it's got to go off and update multiple data stores, do all this work. At this point, we don't really care even how long this takes nose tail. We might care how efficient it is, not so much it's elapsed time, because we've removed it out of the critical path. It's not super time critical now. It just needs to absolutely happen. Another benefit of making your systems function like this as you start breaking it up is you are also improving the testing surface area. If you break off a business piece like process the order like this, you pretty much are forcing yourself to create a contract boundary in your own software of, hey, no matter what, no matter how you do it to collect the order, this is the message we need. It goes in this queue, and then here we process it. Well, that also now means I've got essentially a black box test point here, a feeding request in the order server. I can guarantee an isolation work. I can, if I deploy new versions of this, and I don't deploy of the web server and don't deploy the order server, I can manage my risk. You also, one of the things I personally love, because I love me a good queue, is I've also got a wonderful monitoring point, a beautiful observability point where I can look at the latency of that queue and know how well our overall system is doing. Are we falling behind, or are we getting it? Are we keeping up with activity? In a way that lets me know how we're doing overall without actually holding up customers. If we even have a problem where like our order database is getting crushed, I can throttle the throughput of that. No matter how many orders come in, I can smooth out that flow, which avoids traffic jams. So there's a lot of great benefits for this type of design and architecture. But there are more pieces here, right? Inherently, this is more development work than not doing it. So as much as I love a good queue, and if I haven't said before, I love me a good queue, it's not the first place you go until it's the thing you need to do to solve the problem between asynchronous caching and distribution. Okay. We've waltzed from the front end of the back application to the back end. I've advocated heavily caching, and asynchronous processing, and with a bit of how you can do different distribution, but there's no free lunches. Let's talk about fresh problems we create when we start going through and doing some of these things and moving off the simplicity of just it's a data, it's a single server, web server talking to a single data store. Fresh problems. So this is a classic block of the fallacies of distributed computing, and it's good to remind ourselves and the whole team about this. Even if you're living, your app is running in I don't care if it's running in the top tier cloud, your own data center, the NSA is hosting it for you out of the goodness of their heart, doesn't matter. All of these things are going to happen, are going to end up being true. The network's not perfectly reliable. The speed of light is ultimately going to get you on latency talking between things. You're going to have challenges where things get reconfigured, different things get deployed at different moments, or items change. Something has a single process has its day in the barrel. All these elements of the minute you are out of your own process, because distributed computing doesn't have to mean actually multiple servers running in different data centers or anything like that. It could literally be two processes running on the same box. You will run into all of these same challenges eventually, given time. So when you're looking at your system and thinking through how you design it, you do need to give a nod to basically like never trust the network and some other elements of this that modern frameworks abstract a lot away. But I've been shocked the number of times. For example, I'll talk with a team that's, say, deploying their first SPA app, React or Angular or something, and they don't realize that that's a client-server app. So all the problems we had in the 90s with client-server apps, you can have with SPA. I'll start asking questions about it, like, okay, what happens if I lose my Wi-Fi? It's all running the browser. I lose Wi-Fi, and I get all the way to the point where I'm still filling things in. It's all running locally on my browser. It doesn't realize the network's not there until I hit the order button. Now, if it wasn't a SPA app, then right there I get a hard browser failure. It's kind of what's going on. That's not going to happen in your app. Are you handling that? What are you doing? How are you managing it? What if there's a deployment and the browser version that they're running, that they've got a whole big transaction built up in, now is out of date relative to the API it's calling? So all of these are fresh challenges you get into with distributed computing that you need to think through and have a story around. But I want to zoom in on just a couple of problems because they're brought about by us applying these scale techniques. First one I want to talk about is partial failures. So I've seen this a lot of times in my career. We go through and we add distribution, particularly in the middle tier, right? We've got a bunch of clients, load balancer now, and we have multiple web servers running away talking to our database. And everything is great, except that this guy dies. Now, he might hard die, but maybe it doesn't hard die. Maybe it just stops responding. So in other words, it's not crashed and restarting. It's just becoming a black hole for requests. Well, if I'm using sticky session, you can get a situation where one block of my clients are getting 100% failures, but other people are doing great. Which one do you think your outside monitoring system is probably going to be? Oh, it's going to be the ones going great. And you're going to hear from your own support channel, the app is down. You're going to go, what? Board is green. You're going to pull up your browser and you're going to go in, and which one are you going to get? Oh yeah, you're probably going to get the up node too. So whenever you're introducing, particularly distribution, where you have load balancing across things, you have to worry about partial failures in that middle tier. Otherwise, what happens is you don't find out that it really is down until they all go down, which isn't good enough, right? You've got to do better. And you can't get there. Like I've had a ton of times, like, we use this outside party for monitoring. I'm like, great, but that's hitting the load balancer. All that's guaranteeing is a node is up. That's not nothing, but it's far from everything. So you have to start thinking through how you can handle partial failure scenarios. The more you're using distribution, the worse it is. Again, take my database example. If you have 3 separate data stores all involved in the customer, and they're using, particularly if they're using different server technologies, you really open the door to, like, the Elastic server is down, but the SQL server is up. So some parts of your app work and some don't. What should you do in that case? How do you handle it? It's a fresh set of things you should talk through. That's why we say there's always a cost to these techniques. And so if you scale without doing any of them, you're done. Go on and do more functionality. How do you address it? Well, break your system into those individual failure zones and you need to monitor each instance in that zone for problem. If it's at the web server tier, you're breaking into like, okay, here's the web servers are my failure zone. I need each instance of these. I need to know if they're available or not, because because from the outside, as long as any of them are working, it'll all appear to be working. And now I need to ensure that we're routing around that bad one in the middle. At the end of the day, though, without monitoring, redundancy is worthless. I remember I said we'd eventually talk about using distribution for redundancy. If you don't have the monitoring, you don't find out it went wrong until the last one went wrong. Little story. I got my career started at John Deere. I was working with corporate IT, and we were revving the systems that were going to go down to John Deere dealerships. The big thing we were going to do with this new platform is, for the first time, we're going to give the dealerships the option to have hardware RAID. They'd never had it before. They had disks. If a disk failed, they lost the server, and you had to restore from tape. We were going to use hardware RAID in the service for the first time. And I demoed this to our own support staff and the leadership. I advocated heavily for it by doing a classic thing where I would walk up to the server while I was in the middle of running our big demo, and I would pull out one of the drives and hand it to somebody while it's hot and spinning. If you ever held a drive while it's still spinning, it's got that gyroscopic effect. If it kind of doesn't want to move in your hands, really wonderful effect. Always got a wow. Now, I had gotten my training. I'd come up using compact systems. Compact systems would automatically, the minute you put the drive back in, rebuild the drive. But we were selling HP systems, and I didn't know a key thing, which is that they didn't rebuild that until you told them to rebuild it. And one time, instead of pulling out drive 1, I pulled out drive 6. And we lost everything on the demo server. But there was no alarms, there's no monitoring. I had no idea that the array was running in a degraded state. Without monitoring, redundancy is worthless. All right, another fresh problem, upgrades. The more you're distributing things, now you have a challenge of how do you apply new versions. This can be both a positive and a negative, right? So let's say we want to deploy a new version. Well, if I'm updating all these web servers and we have multiple databases, we have to update all of them. Do you do it customer by customer, block by block? Can you, if you're publishing static content to the browser, you have multiple subsets of these backends that can be running different versions. Can the same static content work with them, or how do you handle it? The bigger you get, the more you apply these techniques, the more you're inducing an upgrade problem. Now, how can we address that? Some basic steps beyond automation, but again, break the system into upgrade zones. Like a tenant can only be one version or another. This is what we do with Loop. A single tenant can only be one version or another. So when we want to upgrade a tenant to something where we change the data store, we actually do a drains, basically park the repository to maintenance, drain it, stop it, upgrade it, verify it, and bring it back online. And then we cut traffic over to the new updated zone. Company I just worked for in a different space, we actually had a CI/CD platform built up so that as long as we didn't change the core SQL schema, we could do everything in flight, so that a given user was either talking to the old version or the new version as it came up, and then we knew we had consistency all the way nose to tail. So the load balancer even knew, like, okay, you're talking the old version. All right, now I'm going to move you to the new version and this set of processes, and you're not going to get a mix of them. That took a heroic amount of work to get going and make happen. It was a real investment. It's not just, oh, we have Kubernetes, you're good. It's more to it than that. So it is, again, a challenge you get into the more you break these things up, the more you apply that asynchronous. So what if you change message formats, right? If I have an asynchronous, I'm writing things through a queue, what if I change the format in the messaging? Because I've added in more features, but I have messages in flight when I run the upgrade. Well, this is where drain, ideally, for example, we would do is stop intaking things. We actually would do it before we started the upgrade. We'd actually stop taking new orders for a few minutes, let all the orders flow through and complete, then put the whole system into maintenance to run the upgrade, verify, and roll. That simplified it. But it's the best big technique if you can't do some of those things is you have to design for that upgrade from the start. So that can be things like not just auto upgrading data stores, but doing things like designing your message formats you're putting in queues So they have a version number header that's above the serialized object that's in the queue, so that your own code can say, oh, this is a version 4 object. Now I know how to deserialize it this way and process it this way. And you basically spread out the removing code and changing code so that you can have essentially adjacent versions in flight in the same code base at the same time until you're confident that an older version will never show up again. It can definitely create a lot of additional complexity to your system. It may be worth it. If you're Amazon, it is worth it. If you're a smaller volume, it may not well be worth it. And all the engineering you're putting into that is engineering you're not putting into capabilities that your customers directly pay for. No customer's picking you because you're really great at your internal upgrades. As long as your system scales and is fast enough that they perceive it as fast enough, that's victory. So, all right, bringing it all home. So, you're going to do these pieces. You're going to pull it all off. It really comes down to testing. Is the system, like for the goals I have from a customer, from my business, do I meet it or not? And if I don't meet it, in which way don't I meet it? Like, is it, oh, it's just these pages. They have performance goals they can't meet because they're doing this other activity. So then what you're going to do is you're going to apply the ACD technique and then test again, ship it, test it. Are you meeting the goals now? If so, stop. If you're not, do the loop again, test again. Because in the end, we have to meet the scalability, but every dollar we're putting into scaling beyond what our business actually needs is waste. All right, core critical lessons learned. The way we scale, ACDC. So async, caching, distribution help us scale. Consistency is ultimately the thing that stops us from scaling. Having that clear consistency strategy for yourself of how you're partitioning data, what latency you're allowing, and thinking that through instead of just taking the default assumption that we tend to in software of absolute consistency nose to tail is what you need to be able to make your system scale, and it'll open doors for you to try out different technologies, incrementally add them, and ultimately evolve your platform over time a lot more effectively. Finally, have that monitoring and management so you can have real data about how well your system is performing. Just because you got to be careful about relying on anecdotal data. Even great systems will have a 99th percentile performance that is uncomfortable. Where one request in 100 is just not as fast as it should be, and for that, you need to have real data so you can say, yeah, but actually, let's look at like our P90, P95 numbers. I like P95 as my fave. Look at our P95 numbers, and they are or aren't acceptable, or it's just in this subset of things that they aren't acceptable in, and that's where we're going to focus our money and focus our energy. And with that, that is the end of the presentation. I'm going to go ahead and stop sharing my screen, cut back the camera. I really welcome anyone's questions and feedback and challenges.
All right, thank you, Kendall. Are there any questions?
All right, so give me at least something for how many folks out there have sat back and thought through scalability problems in the way I laid it out. In particular, we tend to view improving performance as a universal good. Faster is always better. And you can see in this talk, I heavily advocated too, that's only true to the point that it actually benefits your business and they need it. How many folks have advocated from a perspective like that before?
I've started to think about it in that way. There's a sort of a monolith process that I wrote for processing incoming requests. Mm-hmm. And what I've been starting to think about is how would I break that apart, particularly the process of getting new requests versus I have a queue of things that just needs to be worked on. There's
Yep.
not necessarily new requests. And how would I break that apart so that we could be more efficient in the way that we process these items?
Mm-hmm. I've seen some folks, a system I got engaged with a little while back. The previous architect had been super into sagas and mass transit, and everything was horrifyingly complicated. I mean, the code was epic, it was cool, but horrifyingly complicated. Great irony. They were running this on a 16 node cluster to get the numbers. It was burying the database server. But the database they had, which is terabytes in size, went back to the dawn of the company, which meant I was able to actually go back in the database and look at volumes from times past, and saw that in like 2001, it was doing 10 times as many requests on 2 servers as they were doing on this farm of 16. But the difference was that back then they were doing a pretty straightforward, we basically, they had a queue in the database. Like we write a message to the database, it says you need to process this. Another thing had threads that just picked it up and did the work and did it like beginning to end. A lot of business stuff is the one big function. It's the 1,000-line function that says do this, then this. For each of them, do this, then do this, then do this, do this. As long as it's in the background, that can work really well. And when they made it into sagas, they actually made it horrifyingly inefficient because every step of the saga was restoring the earth of stuff into RAM, trying to figure out what the next logical step to do, doing that little increment, persisting it, and requeuing it. To the next thing, do this, repeat the process over and over again. So it was a good example where they bit off so much they bit off a lot of architecture that didn't have actually a business benefit, and in net burned a huge amount of resources, slowing down the system. So there's a lot of truth to the axiom: great complicated systems started off as great simple systems. There's nothing bad about having a monolith that does a thing until it can't do the thing.
Sure.
And then breaking it up, but being really selective, right? Apply the pattern to be selective to okay, what are the boundaries and why? Usually, like usually what it'll be is where there's a great checkpoint of work or something that should be temporarily decoupled. Like, okay, we get to this point now, we have to actually hit the credit card. Actually, that business flow is a really great one. Like, if you do all this work, okay, now we actually have to hit their payment. If they're doing payment with a credit card, they have to hit the gateway. There's all kinds of opportunities for failure at that moment. So having that be a checkpoint, now get payment, is a pretty good design redundancy step, because if there's a problem with payment, you then can easily insert a process of like, oh, the user's credit card is declined. So now I need to email the customer, say, hey, wait a minute, your card got deferred decline. What do you want to do? You can usually find a good business boundary to couple those points, and add real value.
Sure.
Yeah.
Yeah, absolutely. Any other questions for Kendall?
I love me a question.
All right, doesn't look like it. All right, well, thank you very much, Kendall. Great presentation. I've copied the link into the chat for the survey. So if everyone here could please fill that out, give Kendall your feedback. We greatly appreciate that. Remember, it is all anonymous, so good, bad, somewhere in between, let us have it. I will also send that out via email if you happen to miss it in the chat for some reason.
Well, outstanding. Thank you so much for the invite to come speak to the group. I really enjoyed the conversation. And if you have any questions that come up after the fact, please do find me on email or LinkedIn or wherever. Carrier pigeon, whatever works for you. And love to have follow-up conversation. And yeah.
All right, wonderful. Thank you, everybody.